Imagine the ground beneath your feet suddenly becoming a violent ocean wave, shaking everything above it with incredible force. What happens to the essential lifelines that connect our communities, like our roads and bridges, when this happens? Earthquakes significantly impact roads and bridges by causing direct structural damage through intense ground shaking, ground failure mechanisms like liquefaction and landslides, and sometimes direct fault rupture. This can lead to cracks, collapses, and displacement of these vital transportation arteries, making them impassable or unsafe. The primary reason for this devastation lies in the powerful seismic waves generated by an earthquake. When tectonic plates shift, they releases enormous energy that travels through the earth as various waves. P waves, or primary waves, are fast compression waves, while S waves, or shear waves, move with a side-to-side or up and down motion. Surface waves, which arrive last, are often the most damaging, causing the ground to roll and undulate intensely. These vibrations exert immense stress on structures, far beyond what they are designed for under normal conditions, leading to fatigue, cracking, and eventual failure if not adequately prepared. Beyond direct shaking, earthquakes can trigger ground failures. Liquefaction is a particularly insidious threat where saturated, loose sandy soils temporarily lose their strength and behave like a liquid due to shaking. This can cause roads to buckle, bridges to settle unevenly, and foundations to lose support. Similarly, on unstable slopes, seismic activity can trigger landslides or rockfalls, directly burying or tearing apart roads and bridge abutments. In some cases, if a fault ruptures directly beneath a structure, the ground displacement can literally tear a bridge or road segment apart. To mitigate these powerful effects, engineers employ specialized seismic design principles for roads and bridges. This includes using materials that exhibit ductility, meaning they can deform and absorb energy without brittle fracture. Bridges are often designed with flexible joints and bearings that allow segments to move independently during shaking, preventing rigid connections from snapping. Engineers also use advanced techniques like base isolation, where a structure is separated from its foundation by flexible pads or springs, greatly reducing the amount of seismic energy transferred to the bridge deck. Furthermore, foundations are often driven deep into stable bedrock to bypass liquefaction-prone soils. Understanding how earthquakes interact with our infrastructure is crucial. It highlights the incredible engineering efforts that go into building resilient structures capable of withstanding nature's most violent shoves. These design considerations are not just about protecting property. They are fundamentally about ensuring that critical transportation routes remain safe and functional, allowing emergency services to reach those in need and communities to recover quickly after a seismic event.